Welcome everyone. We'll be talking about QoS refinements for background operations using MClock today. So what is MClock? MClock is an algorithm for I/O resource allocation that we use in Ceph. It's described in the paper that I've linked over there, so in case anyone's interested, they can look that up. Distributed MClock has its own Git repository and it's imported as a submodule in Ceph. So we use MClock in Ceph to allocate I/O resource to its services. So from MClock's perspective, each Ceph service is a client. So like you can see in that diagram over there, one service is for external clients, one is for background recovery, and the third is for background best effort. This includes all the other background operations such as scrubbing, PG deletion, and snap trimming. The IOPS capacity of an OSD is the IO resource that is shared between the Ceph services. So before going deeper into MClock, just a brush up on what about WPQ. So the weighted priority queue was the previous scheduler that was being used by Ceph OSDs. In WPQ, each operation that was being enqueued had a priority and a cost associated with it. And WPQ used these parameters to determine the dequeuing order of these operations. What this meant was that operations having a higher priority and a lower cost would spend lesser time in the queue compared to an operation that had a low priority and a high cost. So what exactly was cost from WPQ's perspective? So cost basically is a parameter that gives an estimate of how expensive it is to process that particular operation. And in case of WPQ, this value was static. So there were configuration values such as OSD PG delete cost, OSD scrub cost, which defined what the cost of an operation was. So drawbacks of WPQ. WPQ does not have the ability to allow users to set any kind of resource allocation, so it's tough to use for QoS purposes. It also doesn't differentiate between the kind of operations in the way that I mentioned MClock was, and it only cares about the priority of an operation. Due to the lack of resource control options available in WPQ, there have been a lot of configuration options introduced over time to try and control background operations. An example of this is the various sleep options available, which were introduced to control the rate of recovery, scrub, snap trim, and PG deletion. And another example is the large costs that are set for recovery and scrub operations to achieve throttling them. So looking a little deeper into MClock. So like I mentioned before, MClock uses the total IOPS capacity of the OSD. And that's the resource that is being shared between the Ceph services. So the QoS controls that MClock uses to allocate these IO resources are 3 parameters. The first one is reservation, which defines the minimum IOPS that will be allocated to a particular client. The second one is limit, which defines the maximum IOPS that will be allocated to a client. And the third one is weight. So weight comes into play when all clients have received their minimum reservation and there's extra capacity. The proportion in which that extra capacity should be allocated between the clients is determined by the weight parameter. So MClock has some inbuilt profiles that help in allocating the resource. Currently, there are 3 profiles. The first one is balanced. The second one is high client ops, and the third one is high recovery ops. So each of these profiles have QoS controls set to try to achieve higher client ops or higher recovery ops. Or in the case of balanced, we try to give an equal distribution to recovery and client ops. Sorry. So why MClock? Right? It provides predictable allocation of resources to services through the QoS controls mentioned. And it improves user experience because there are intuitive MClock profiles available. So it's easier to switch between the profiles than actually go and change configuration parameters to achieve higher recovery ops or higher client ops. It's hands-free, which so there's no need to tune multiple Ceph options to achieve the desired resource allocation. And it's flexible. So what flexible means is that there's also an option of a custom profile in MClock. So if you know the workings of MClock well enough, you can create your own profile to achieve, say if you want higher scrub ops, which is not a profile currently, you can build your own profile to do that. So what is the difference between MClock and distributed MClock? Currently, MClock is used for QoS for OSD operations. So this is the non-distributed version of the MClock algorithm, and it's only for the internal Ceph clients. It doesn't establish fairness between the external clients. QoS for external client operations uses distributed MClock. So the difference is that there are two more parameters that it uses called delta and rho, which keep a track of how many reservation requests have been completed and what are the total number of requests to achieve fairness between external clients. So just taking a look at MClock in Ceph. In 2018, I think, was when the DMClock submodule was created. And there was the initial implementation of the MClock scheduler. And also initial work started on client versus client QoS. In 2019, we started looking at how we can adapt MClock scheduler for Ceph. So this is when we started coming up with ideas for MClock profiles and taking a deeper look into what needs to change in the Ceph code to use MClock. So one of these changes was classifying push messages as recovery messages. In 2020, I think Sridhar started looking into client versus background recovery. So we ran tests with client and recovery operations running in parallel to verify the multiple MClock profiles and see if they provided the quality of service. The year after that, we started looking at other background operations as well, such as scrub, snap trimming, and PG deletion. And we also started working to revive the client versus client PR mentioned before, because there had been a lot of changes over the years. And towards the end of last year, we detected a slow backfill issue in larger scale testing of MClock. So now coming to the current state, we started working on debugging the slow backfill issue and taking a deeper look into the recovery and backfill internals and how we can adapt them to work better with MClock. Part of this was taking a deeper look into the MClock cost modeling. Okay, so these observations were from the initial tests we ran. So this was all with the default cost options. And we ran multiple tests with client operations and background operations running in parallel and compared the results with like MClock versus WPQ. In client versus recovery tests, what we noticed was that backfills were slower and recovery was slower, and higher latencies were experienced by external clients. On the scrub side, we noticed a similar scrub rate with WPQ and MClock and client performance as well. But that's not exactly what we wanted, especially if high client ops profile was used. We wanted client ops to perform better. In client versus PG deletion tests, PG deletions were much faster in MClock than in WPQ. This could be because of the sleep option being disabled in MClock by default. But because PG deletion was happening much faster, client ops were compromised while PG deletion was going on. And in client versus snap trim testing, the results showed lower than expected throttling of the snap trim operations. So the inferences we drew from these test results was that MClock is very sensitive to the cost assigned to an operation. So the previous method of assigning a static cost would not work with MClock because we need the cost in MClock to actually reflect the size of the I/O. An example of this is OSD recovery cost is set to 20 megabyte regardless of the size of objects being recovered. And this was causing recovery operations to remain in the queue for a really long time, even if the object size being recovered was really small. And also, reply-related operations had the same cost associated with them, and they were therefore throttled. Another observation was that PGs with degraded object versus PGs that just needed backfilling were given the same treatment. This was a change that we had to make on the Ceph side because we wanted PGs with degraded objects to backfill much faster. The mechanism of allocating QoS controls via the profiles was complicated. So we needed to mention the IOPS allocated to each of the clients. And this is a little complicated because you also have to take into consideration the number of shards in an OSD when you calculate that. And we wanted to simplify it. And yeah, the last thing was that the MClock profiles needed to be optimized better depending on the purpose they were being used for. I think, Sridhar.
Yeah, thanks, Aishwarya, for the background that you provided. So, so we can now kind of get into a slightly more deeper dive into the MClock algorithm itself and the MClock scheduler and the purpose of MClock scheduler. So before we get into the nitty-gritties of the MClock algorithm itself, there's an entity called as the MClock scheduler, which is basically a replacement of the WPQ scheduler. So the purpose of the MClock scheduler is to enqueue the various classes of operation that Aishwarya already talked about into the MClock queue. But the other thing is we have operations that require immediate attention. For that, what MClock maintains is separate priority queues. Right now, if you see, there is a immediate priority queue and a high priority queue that was recently introduced by Aishwarya. So in the immediate queue, essentially what happens is all the reply ops, essentially they are also called as sub-ops, sub-reply ops, all those are basically enqueued into the immediate queue, and that queue is not handled by the MClock algorithm. So those specific operations are given immediate priority so that client operations are not experiencing any latency. So the diagram essentially tells us about the NQ and the DQ operation. When an operation is enqueued, the priority of that specific item is checked. If the priority is set to an immediate class of operation, that specific operation is enqueued into the immediate queue. But if the class of operation is classified into any of these categories, the client, recovery backfill, scrub, or snap trim, those get into the MClock queue. And we have essentially represented that as a dotted box, meaning that it's silently sitting in the background and it does most of the legwork. So, yeah. So the high priority queue is currently introduced in the main branch. It's still not backported to Quincy or any other releases at this point. So we are yet to test that. So it will probably take a few more days for us to actually test. And the intent of having the high priority queue is for some other purpose. For example, you could have a PG which is in pre-merge state and which is in backfill wait, for example, and those specific PGs need higher attention when compared to other immediate ops that you see here. So those specific changes are yet to be made, and we hope to make that in the coming days, and then make that available. So yeah, let's get into the MClock tags and the scheduling phases of the MClock algorithm. So as Aishwarya already mentioned, there are 3 QoS controls, which is reservation, wait, and limit. The wait is also classified as a proportional tag. So the purpose of having these 3 tags is to allow the algorithm to provide predictable allocation of resources. The basic principle behind this is the algorithm basically allocates the minimum reservation meant for that specific resource, and that reservation should be proportional to the share that is set for that specific service, and the allocation shouldn't cross the limit that is specified as part of the profile. And as far as the scheduling itself is concerned, scheduling is performed in 2 phases. So the first phase is the constraint-based phase, also called as the reservation-based phase, and the second phase is the wait-based phase. So let's take a deeper look into what these 2 phases mean. So I've tried to represent the algorithm in a most simplistic way. So I have divided this into the constraint-based phase and the wait-based phase. So the algorithm essentially first checks if there are any reservation tags which is less than the current time, and the way it does is through a tag increment operation, as I have represented here. So it basically shows that the tag increment, which is r prime is nothing but the value of the previous r tag plus the inverse of the reservation of the requesting service. So the addition of this, if it is less than the current time, it means that the client has still not reached its upper limit, and so that specific request from that client can be scheduled. So the algorithm, if it finds such a request, the algorithm ends at this point, and that specific item is returned from the queue. If not, that means there are no clients which satisfy the reservation criteria. That means all the clients have crossed the reservation limit. So the algorithm shifts its phase into the wait-based phase. So in the wait-based phase, a couple of things come into the picture, which is the first one is the limit. So the algorithm next checks if there are any clients having a limit less than the allocated upper limit. If so, the request with the minimum p tag or the share tag is selected, and after that, the r tag of that service is reduced by 1 over r. The reason why we do this reduction of r tag of the service is to maintain the condition that all the requests from a specific client should be spaced 1 by r apart. So that's the basic condition that needs to be maintained at all times. So once that is done, that specific request is returned from the queue, and that item is scheduled. So this in a nutshell describes what the algorithm does. So what did we do? So that's the bare bones algorithm. So what did we do next? As Aishwarya mentioned about cost, so the cost comes into the picture here in a very crucial manner. So and if you look at the paper of MClock, they also allude to this fact about handling cost based on the IO size. That's very critical. So if you look at the modification in the formula, earlier it was r prime plus 1 over r. Now what we do is incorporate the cost into this formula, and it will become r prime plus the cost over r. So the cost of that specific operation now plays a crucial role as well. So what does it actually mean? The larger IO sizes will essentially take longer time to complete. So we need to accord the cost for those operations accordingly. So, and if the cost of a specific operation is very high, it means that that specific item will stay in the queue for a longer time. Yeah. But how do we arrive at the cost? So we took the OSD itself, the properties of the underlying device. So it will have a specific random IOPS capacity, and also it will have the max sequential bandwidth capability. So we consider these two parameters and arrive at a parameter called cost per IO. So this will be a constant for a specific device. And what we do is add the IO size to this cost per IO, and then it will be in bytes essentially. And this is passed down to the MClock algorithm, where it uses it to calculate the calculate when the op can be dequeued from that MClock queue. So this portion of the cost calculation was causing the delays that Aishwarya mentioned earlier. So because of the static cost that we allocated for recovery, scrubs, and other operations. So no matter the size of the object, the cost, because the cost is static, the scheduling as a result will be static in most cases, which is why we were not seeing the intended response from the MClock queue. So from the inferences portion, we identified key changes to be made to adapt to the MClock algorithm. And the first, obviously, is the cost. So what we do is now take the average size of the objects in the PG. So that will be like a realistic indicator of the size of the objects in the PG, and that is set as the cost for the recovery. So since it's now going to be dynamic, recovery rates will now vary and is directly proportional to the average size of objects in the PG. And what we noticed was the recovery push and pull reply operations. They were accorded a relatively high cost with WPQ, but now that's not the case. With MClock, what we do is we don't allocate any cost to these operations. Essentially, what we do is set a min cost for these operations, because most of the legwork is already done as far as recovery is concerned. So we need not throttle the reply operations any longer. So as a result, we expect to see faster recovery completion, and it also has the added benefit of clients being able to access the objects, a recovered object, much sooner than before. The next thing is the key differentiation between degraded recovery versus backfill. So when you have objects being degraded, that means you have lesser copies than what you have configured. So those specific PGs need to be given higher priority, as opposed to misplaced recovery, where you are just trying to move data from one PG to the other, or from one OST to the other. So now the backfill operations are given slightly lower priority, and degraded recovery objects are given much higher priority. So in addition to the cost changes, what we did was we optimized the 3 built-in profiles accordingly. So I'll discuss that in the next few slides, and it's described in a tabular fashion that will be clearer to see. The other important thing that we did was to simplify the specification of QoS controls in the profiles. Earlier, like what Aishwarya mentioned, we were setting these QoS controls in terms of IOPS, and the users were required to understand how many shards were there in the OSD and accordingly set those values, which doesn't seem user-friendly. So what we did was the QoS controls will now be specified in terms of a simple proportion in the range 0 to 1, with 0 being, if we have a reservation of 0, it means that there is no minimum lower limit for a service, and a limit of 0 means there's no upper limit that a client can use. So 0 means different things in terms of reservation and the limit parameters here. So hopefully these changes will improve the user experience, is what we hope, and any feedback here is really appreciated. Once the code gets merged. So looking a bit deeper into the MClock profiles themselves. So earlier, the high client ops was the default profile. But we discussed it further within our team, and we felt that the high client ops can be it'll be like a one extreme, and high recovery ops can be the other extreme, and we need to have a different profile which is somewhere in the middle, and we thought that the balanced profile would be a good fit for that. So here what we do is give equal allocation for both client and background recovery. As you can see here, I represented the proportions in terms of percentages for better clarity. But actually, when you specify it, you should be specifying this in terms of ratios, like I already mentioned. Yeah, they get a reservation of 50% each, and there's no maximum limit for client and background recovery. Whereas the background best effort clients, they will get no reservation. That means if there are no if there are no background recoveries going on, for example, the best effort client can use as many reservation as it requires. The high client ops is one end of the spectrum, where the client ops get really high reservation and weight, or the proportion, and the background recoveries get the lowest reservation. So this could be useful in cases where you have a IO intensive workload that is suddenly alive in your cluster, and you want clients not to have not to experience any high latencies. So in those cases, an operator or user can enable this profile for that duration of time. Now the other end of spectrum is you have a lot of recoveries going on, and when the cluster is lightly loaded in terms of client ops, the operator can choose to enable high recovery ops, where recovery operations are given higher priority, as you can see here, with high reservation of 70% and with a higher weight of 2. So, what are you doing on time? Yeah, so what we did was we tested this on our internal lab setups. Right now, the result that I'm going to present, it was tested on a small scale on one node with this configuration. It had basically 4 NVMe SSDs, Intel P3700 series SSDs, and about a handful of Seagate Constellation drives. And all the code changes that we made, it was merged into Quincy tip, and then we tested this on that setup. The test methodology, what we used was basically CBT, the Ceph benchmarking tool. It already had a recovery test, so what we did was we enhanced that test to cater to this specific use case, where we create degraded recoveries and backfill as well, and then use FIO to run IOs on the client pool, and then measure all the metrics that we wanted to. So what we also did was, as a baseline, we executed the same test on WPQ to establish the baseline, and then later use it for comparison purposes. The test steps essentially involved, like I mentioned, creating 3 pools. All these are RBD pools. The pool A was configured as a client pool. The other 2 pools was a recovery pool with large objects, one pool containing large objects predominantly, and the other pool containing small objects. The client pool was pre-filled as well, and then an OSD was failed. That leads to obviously degraded object recovery. So when the recoveries are going on, we collect all the metrics related to that, and then once the OSD is down, what we do is fill up the other 2 pools, the recovery pools, with large and small object sizes, like what's mentioned here, and then once that is done, we initiate client IO on the client pool. In this case, what we do is the test that we performed is predominantly 4K random writes, and which is 60% rate limited. We essentially used FIO to do this. The idea being clients would not always be running full throttle to saturate the disk, so we thought that 60% rate limit of that specific client op is sufficient. Once the client ops are started, what we did was bring up the downed OSD. So what this does is start the backfilling process. And once the backfilling starts, we again start to monitor and collect all the necessary metrics. So, yeah. And what do the results look like? So this is what is the most interesting part. So as you can see here, first what we did was to measure the recovery metrics using the backfill metrics using WPQ. The number of misplaced objects recovered was around 145,000 in this small cluster. This is true across all the profiles for true comparison. You can see that with WPQ it took about 6,080 seconds to recover the entire set of misplaced objects. With high client, as expected, recoveries get lower priority, and you can see that it took a slightly longer time to do the recovery. But with the balanced, which is the default profile, interesting results where we see that recoveries happen much faster than what we see with WPQ. That's about 8.25% faster, right? Yeah. And obviously, with high recovery, where recoveries are optimized, it is approximately 50% faster, as you can see here, and corresponding increase in the object recovery rate. And this chart is pretty self-explanatory. So we chart the progress of recovery over time, and you can see that high client takes the longest, followed by WPQ. Balance, it's somewhere in the middle, and high recovery ops takes the fastest time to recover the objects. So good results so far, but what does it mean in terms of client ops? How did client ops did the client ops get impacted? Let's see that. You can see the baseline at 60 was those values. The one in blue is the completion latency, followed by the 50th percentile, and all the 95th to 99.5th percentiles. That's what is plotted here. You can see, for comparison purpose, you can see that the high client, the completion latency for the high client is is slightly better compared to WPQ. The 50th is slightly longer, but not by much. It's still comparable. The tail latencies are again pretty much comparable, if not better, in most of the cases. And the most important thing is the balance profile. You can see that the numbers here are pretty impressive, considering that the recoveries happened much sooner than what WPQ performed. And of course, high recovery showed the highest client latency as expected. And similar tests were performed with SSDs as well, and we see similar kind of results. With WPQ, we got around 700 seconds to recover about 550,000 objects. With high client, it took the longest time, followed by balanced and high recovery. And the interesting thing is the recovery times for high recovery and WPQ are almost comparable. And the same thing, we plotted the backfill recovery rate over time. The interesting fact is the WPQ and the high recovery, they are almost the same. The blue and green have kind of merged into a teal color now. So it's like the same recovery rate that we see, which is interesting. This chart is is a historical chart where we can clearly see the effect of slow backfills. You can see the long tail here. It took a long time for the recoveries to complete, and I believe if you compare it with the previous chart, you can see that more or less I think we have addressed the slow backfill issue. So that's the interesting portion. And of course the latencies. You can see that across all the MClock profiles, you see that the latencies are better when compared to what we see with WPQ. And the most interesting part is with high recovery profile, we see that the latencies are better across all the other profiles, which is an interesting statistic. But we need to go back and test it on a scaled setup so that we get a better idea of how things look like when things are scaled. Another interesting thing is the client, the 50th percentile latency comparison across all the profiles. The interesting portion is the initial latencies are slightly higher. That's when the degraded recovery was happening. And then once the backfill started across all the profiles and WPK as well, you can see that the latency slightly dropped and they stayed consistent over a period of time. Yeah, you want to talk? What's good?
Yeah, I'll just cover this quickly. So we ran similar tests for scrubbing as well. And we could see that with high client ops, scrubs are slower because we limited the background best effort client. So that's exactly what we wanted. And in high recovery ops, we placed no limit on the background best effort client. And we saw similar performance to WPQ. So we could see that high client scrubs taking the longest time. And we wanted to see what the effect on the client ops was. And yeah, if you see the throughput values, the IOPS, you could see that high client profile did much better than WPQ and the other MClock profiles. So basically the cost changes and the changes in the MClock profiles helped achieve this. You can conclusion.
Yeah, so the final slide. So what conclusions can be derived from this? We made quite a few considerable efforts, and the feedback from the team was really valuable. Sam, if you're around, so the feedback from Sam and contributions from Sam were really helpful in identifying the last bit of code changes to resolve the slow backfill issues. So we're quite happy and confident that when we test it on scale, we're going to see similar numbers. And we should be able to make this available in the coming downstream release, hopefully. The other interesting thing is the MClock profiles are more user friendly. So this ties in with the efforts to make Ceph more user friendly, less config options to configure. There are a ton of sleep options and other cost-related options that people used to modify with WPQ, and we believe that with only MClock profiles, the operators or users should be able to manage the recovery and the client load more effectively without worrying about a ton of knobs and buttons. As we saw, the results with SGDs and SSDs show promising results. And the next step here is to actually do some large-scale recovery backfill testing. That's on the pipeline. And also for other background operations like scrubs, snap trim, and PG deletion, we hope to make similar kind of code changes and hope to see a similar kind of results as we did with recovery. And the last bullet point, of course, is for the QoS across the LibreDOS clients. This ties into the multi-tenancy and the rate limit and the fairness portion of it. So that's still a work in progress. I believe the LibreDOS APIs are ready, and the PR associated with that is also reviewed. All that we need to do with that PR is to get some tests going with multiple clients and see how the results look like. And medium term to long term, we hope to introduce QoS for RBD, RJW, and CephFS as well. So, yeah. Questions?
Hello? Yeah, now it works. Thanks for the presentation. There's already a way to incorporate the I/O size in the cost, would you also be able to differentiate or give a cost to, like, for example, read operations or write operations? So you can actually favor reads over writes or other operations?
Yeah, I
in
think.
theory?
Yeah, yeah. I think right now we don't differentiate between reads and writes. Any I/O that comes in, depending on the size of I/O, the MClock will go and provide the QoS for you. We don't differentiate right now. We don't differentiate reads and writes. Yeah.
But in theory, the framework would allow you to do so, if it would make sense, of course.
Perhaps yes, yes.
All right.
We can make those changes. Yeah.
So if I understand correctly, when, let's say, a client op comes in, the only thing that you consider in the timing, in the scheduling of the client op is the one previous client op. When did just the previous client op happen?
Yes.
You don't consider any kind of history. Just the very recent one.
Yeah, the
so
previous
that
tag.
kind of works well for FIO because FIO submits the IO like boom, 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 like a clockwork. But in the realistic scenario, IO is much more bursty. So wouldn't it be advisable to kind of consider maybe a bit more of a history? Like, for example, if no client ops come in, and you get 2 client ops, then those 2 client ops are fair to execute immediately. Versus if lots of client ops came in, then the client op should wait.
It actually does.
Yeah, yeah.
It's a little bit more complicated than just one IO. It keeps a scaling at a counter that represents time bounds in which you're allowed to do things. Depending on the category.
Yeah, I think this ties into the idle credits, right? If any client is idle for a while, MClock doesn't give it any credit, and it goes ahead and actually assigns the last recovery tag to that client which just got active and started doing IOs. So it accounts for that. Any other questions? Yeah.
I have a question about bug fix PL of the MClock. So with the MClock recovery backfill cost fixes, the recovery backfill cost fix patch PL has not merged yet. And I'd like to know how serious this bug, how the seriousness of this bug, because I'd like to tune the MClock by changing the MClock parameter. So if this fix is very serious and breaks completely the current 70.2.6 MClock is completely broken, the delay the evaluation of MClock configuration, but it is not so serious and just the current MClock is not so not identical. I'll continue to evaluate the changing these parameters.
So yeah, if I understand the question correctly, you plan to use MClock and modify the parameters yourself. You want to experiment with that, and you want to know whether the current patch that you're working on would that be merged anytime soon, so that you can use it for your purpose. Is that right? Yeah. So the depending on the results that we see, they do look promising. The only thing that's pending is to test it on a scaled environment, and if the testing there shows good results, I think that patch will find its way into the next Quincy release, and possibly downstream as well. So, yeah, then you can probably start using it for your purpose.
Yeah. Thank you very much.
Any other questions? Yeah. Thank you.